Then moving on to the next topic, that is Archimedes principle. Now this particular Archimedes principle, it is used to find the purity of a particular substance, or basically in the first instance, Archimedes principle was discovered to find or to calculate the purity of gold. Now everyone, we might have read about the number of stories that you come across in the case of your school textbooks, how this particular Archimedes principle came into picture, how he was able to discover this, right? So there in that case, the first and foremost thing, it was used for finding out the purity of a particular substance. In the earlier instance, it was used for finding out the purity of a gold, right? Now according to this particular principle, suppose that if I'm taking the case of a beaker which is consisting of water up to this particular level, right? Up to this particular level we have got certain amount of water in this. Now this particular beaker has got an opening at the side. This is a sideway opening. Now into this particular beaker which is consisting of water, you are placing an object in this one, an object which is having a weight of something around 5 kgs. The moment you are placing this particular object which is having a weight of something around 5 kgs, the water which is present in this beaker starts overflowing through the side channel, through the outlet, and the water that is coming out is collected in the next side beaker, right? You have got another beaker here in which you are collecting this particular water. If you measure the weight of this particular water which is present, which is collected in the next beaker, the weight of the water that is displaced, this is nothing but the water that is displaced. The weight of the water that is displaced is equal to the weight of the object that is immersed in water. So Archimedes principle states that whenever an object is immersed in water, this particular object will displace an amount of water which is equal to the original weight of the immersed stone. Now here in this case you are immersing an object which is having a weight of 5 kgs. Now this particular water which is having a weight of 5 kgs is displacing an equal amount of water. Even this particular water, if you weigh, it weighs 5 kgs. Right? An object which is immersed in water will displace an amount of water equal to its weight. This particular fundamental thing is what we call it as Archimedes principle, and this particular Archimedes principle is used to find out the purity of a substance, the purity of a gold. Now based on this particular Archimedes principle, right, we talk about some of the objects which are floating in water, some of the objects which sink in water, right? Now if at all we see that, if at all the density of the object, if density of object is less than the density of liquid, if density of object is less than density of liquid, then in that particular case the object will float in water. The object will float in water. If at all the density of object is more when compared to the density of liquid, in that particular case the object will sink. Suppose that if the densities of both the substances are equal, object density as well as the liquid density both are equal, in that particular case the object will partially float. The object will partially float, which means 50% will be inside water, 50% will be above the water. So here in this particular case, it depends upon one particular thing called as density of the liquid, density of the object. Now for example, suppose that you take a small iron nail, right? That particular iron nail, the moment you drop in water, it immediately sinks. But if at all you are converting that particular iron nail into a very thin foil, and that particular thin foil, the moment you drop in water, it starts floating in water. Now there in that particular case, it depends upon the density of that one. What is density? Density equal to mass by volume. Density equal to mass by volume. Suppose that if at all I am talking about nail, right? Iron nail. So when talking about the case of iron nail is having lesser amount of volume. As the volume is decreasing, density is increasing. So if at all the density of the object is more with respect to density of the liquid, then the object has to sink. Then the same material, the same iron nail, you are converting into a very thin foil. The moment you are converting into a very thin foil, in that particular case, the volume will increase. If the volume is increasing, density is decreasing. So if the density of the object is less than density of liquid, then in that particular case, the object has to float in that particular case. Object has to float. So here if the density of the object and density of liquid both are same, in that particular case, the object will partially float. The object will partially float, right? And based on this particular thing, we talk about certain materials, certain substances, how they float or how they sink in water, right? Now for example, you're talking about the case of a block of ice. A block of ice when placed in water. A block of ice when placed in water. Suppose that this is a beaker which is consisting of certain amount of water up to this particular level, right? When there is no ice, the water is present in the beaker up to this particular point. The moment you are dropping a block of ice in this, the moment you are dropping a block of ice, then immediately the water level will rise up to this particular point. Because of the weight of the object, the weight of the ice that is present in water, the water level is increasing. The question will be the simple one, very straightforward, right? When a block of ice in water melts, then what happens to the water level? Now here in this case, what we have drawn here, you are placing a block of ice in water. When a block of ice is placed in water, water level will increase, right? At the same time, when a block of ice melts in water, the water level will remain the same. The water level is not increasing, the water level will not decrease, right? At the same time, suppose that Archimedes, right? Suppose that if at all you are traveling in a boat, you are entering from river water to sea water. Whenever you are traveling in a boat, suppose that this is up to the case of your sea water, and at the same time this particular point, this is the case of the river water. The boat is like this. Now here in this case, whenever you are traveling in a boat in river water, the boat is submerged to a larger extent. The moment the boat enters from river to sea water, then in the case of sea water, the boat is submerged to a lesser extent here. Here in this case, you can see that very clearly that in the case of river water, the boat is submerged to a very larger extent. But whereas in the case of your sea water, the boat is submerged to a very lesser extent here. The reason is that the density of sea water is high. Right, here in this particular case, the density of sea-water is high when compared to river water. If you are comparing the river water as well as the sea water, river water is having more density. Whenever you are comparing sea water and river water, sea water is having more amount of density. Why? Because of the presence of salts and minerals. Now here in this particular case, river water is almost pure. That is the reason why here in this particular case, the presence of salts and minerals in this one is less. As a result of which density is less here. Now, whenever a boat is entering from river to sea, since the sea water density is high, it tries to push the object in the upward direction. As a result of which, the boat will be at this particular position submerging to a very smaller extent. But wherein, in the case of your river water, since the density of river water is less, the object will be submerged to a very larger extent. At the same time, when talking about the case of swimming, swimming is easy. In sea water because sea water is having high density. That is the reason why the object or the body will be pushed upwards. As a result of which, swimming is easy in the case of sea water. But whereas in the case of river water, swimming is difficult because river water is having less density, as a result of which the human body, the object will be pushed inwards, as a result of which river swimming is easy in the case of sea water when compared to the river water. Now this particular thing called as Archimedes principle, it is used for finding out the purity of a gold, at the same time when an object will float, when an object will sink in water. So there in that particular case, right, this is the case. Now here a person is trying to swim here. So whenever he is trying to swim, he is trying to exert certain amount of force in the downward direction. At the same time, there is an amount of force which is acting in the upward direction, which you call it as a thrust. As a result of it, the object will be pushed upwards. So when you're trying to swim, in the case of sea water, the pressure that is acting in the upward direction will be more, as a result of which the object will be pushed upwards. But in the case of sea water, since the density is less, the amount of thrust that is acting will be less, as a result of which the body will be pushed inwards. Now here is the case here. Now here in this particular case, you are having a beaker like this. Now this object is present at this particular point. The moment this object is placed in water, the water level is increasing. If you observe this one, it's very clear that here it is, the bowl is completely empty. The bowl is completely empty here. The moment you are placing the object, the water level is increasing here, and you find certain amount of water in this particular beaker. So the weight of the displaced water is equal to the weight of the object that is immersed in this one. Upward thrust is equal to weight of the liquid that is displaced. So weight of the object that is immersed in water is equal to weight of the liquid that is being displaced. Then here in the case, if the weight of the immersed object is greater than the upward thrust, the object will sink. In simple terms, you're talking about the case of density here, right? If the density of the object is more than the liquid, the object will sink. If at all the density is equal to, in that particular case, the object will remain at the same level, the object will float. But whereas if at all the object density and the liquid density both are equal, in that particular case, the object will partially float. If at all both the densities are equal, then the object will partially float. If at all the object density is less than the density of liquid, then in that particular case, the object will completely float. If they are equal, it partially floats. If the density of the object is less, then the object will sink in that particular case. In this particular case, you can see that one object is completely sinking here, one object is completely floating, one object is partially sinking. Right? Here in this case, object density, liquid density both are equal. Here in this case, object density is high when compared to liquid density. Here in this particular case, object density and liquid density are partially equal. In that particular case, different cases. So here in this case, object density, liquid density both are equal. That's the reason why it's partially floating. Object density is less than liquid density, object is completely floating. Object density is high when compared to liquid density, object is completely sinking. Different cases, right? Then we'll move on to the last topic in the case of your mechanics, that is motion. So when you're talking about the case of motion, so here we're talking about the different types of motion. Generally when talking about motion, we talk about the different cases. Suppose that when you're moving on a straight line path, you call it as a linear motion. When you're moving in a curved path, you are moving in it's a curved motion, right? Rotatory motion, you call it as a rotatory motion. At the same time, suppose that if you are moving between two fixed points like this, nothing but executing to and fro motion, then you call it as an oscillatory motion. So different parameters. Now this is what you call it the oscillatory motion, where the pendulum is doing some oscillations between two fixed points. Now here you can see that a satellite, this is a satellite which is moving around Earth, this is doing a circular motion. You talk about the case of a fan, ceiling fan, it is continuously moving about its own axis. It is what you call the rotatory motion here. At the same time, here in this particular case, the moment you kick a ball, the ball is moving in this particular motion, which you are calling it as curvilinear motion. As long as you are moving in a straight line, linear motion. Now at the same time here, this is two fixed points. between two fixed points, you have got some particles which are moving like this, or else you can even say the particle is continuously vibrating between two fixed points. That is what you call it as vibratory motion. So the motion will be having the different types of motion. So in that one, the first one, we're talking about the periodic motion. So we're talking about the case of periodic motion, a motion which is repeating after regular intervals. That is what you call it as a periodic motion. Now suppose that in the case of your periodic motion, you're talking about the case of motion of Earth around the Sun. When talking about the case of motion around the Sun, Earth takes around 365 days to complete one rotation. Moon takes 24 hours to complete one rotation on its own axis. So this particular period of 365 days, or else 24 hours, or else the hand's clock, the seconds hand in your watch, it takes around 60 seconds to complete one rotation. So this particular value of 60 seconds, or else 24 hours, or else 365 days, this is a fixed value. So a motion which is repeating after regular intervals, that type of motion is what you call it as periodic motion. You can give other examples. The needle of a sieving machine, it just keeps on moving up and down continuously. At the same time, the motion of a pendulum always keeps on moving between two fixed points. So these are all the examples for your periodic motion. At the same time, you're talking about oscillatory motion. So in the case of your oscillatory motion, you're talking about the case of your to and fro motion of an object. That is what you call it as oscillations. So when talking about the case of oscillations, right? So when talking about the case of oscillations here in this particular case, when talking about the oscillations, so oscillations, you can give some number of examples. For example, the needle of a sieving machine. The needle of a sieving machine, it always keeps on moving up and down between two fixed points. That's the reason why you're calling it as an oscillatory motion. At the same time, the simple pendulum always keeps on moving between these two fixed points. That is the reason why we call it as an oscillatory motion again. So when talking about this motion, the motion can be of different types. One is periodic, the other one is oscillatory. But in the case of your oscillatory motion, you're talking about to and fro motion. To and fro motion what? Between the two fixed points here. So as long as an object is moving between two fixed points, you call it as an oscillatory motion. If it is moving in a continuous circular path, you call it as a rotatory motion, or else you call it as a circular motion. Right? Then, when talking about the case of oscillatory motion, we talk about one particular thing called as SHM. We talk about one particular thing called as SHM. That's nothing but the simple harmonic motion. So what is this particular simple harmonic motion? Now, whenever an object is executing some motion between these 2 points, right? An object is moving between two different points such that the displacement is directly proportional. The displacement of the object is directly proportional with respect to the force that is acting on it. On every particular simple pendulum, there is certain amount of force that is acting. Now we have seen. So whenever you're talking in the case of a simple pendulum, at this particular point, it possesses only potential energy. At this particular point, which you are calling it as a mean position, it possesses only kinetic energy. So here in this particular case, the amount of force that is acting on the object is directly proportional to displacement, right? So there in that particular case, you're talking about simple harmonic motion. So in the case of simple harmonic motion, there is one type of force which you're calling it as restoring force. The restoring force is directly proportional to displacement. If at all the restoring force is more, then in that particular case, displacement will also be more. If at all the restoring force is less, displacement will also be less in that particular case, right? Then, now when talking about this particular periodic motions, right? Simple harmonic motion as well as periodic. A motion that repeats itself on a regular cycle, we call it as periodic. So in the case of simple harmonic motion, restoring force is directly proportional to the displacement that is produced. Now, in the case of simple pendulum, right? In the case of simple, we talk clearly about, specifically about simple harmonic motion. Now, this is the case of a simple harmonic motion, or this is the case of a simple pendulum. A pendulum, when it is at this particular point, you call it as the mean position. This point, this is what you are calling it as the extreme points. Mean point, extreme point. At the mean point, kinetic energy is maximum. At the extreme point, potential energy is maximum at the extreme point. At the mean point, kinetic energy is maximum at the same time. So in order to complete one oscillation, to and fro motion, the time taken to complete one complete oscillation, that's what you call it as a to and fro motion, that is what you call it as time period. And the time period of a simple pendulum is given by t equal to 2 pi into under root L by G. T equal to 2 pi into under root L by G. This is an equation for the time period of a particular simple pendulum. Now from this particular equation, it is very much evident, very much clear that the time period of a simple pendulum is directly proportional to square root of its length. At the same time, the time period of a simple pendulum is directly proportional to 1 by root G. Or else you can even say time period is directly proportional to square of its length. Time period is inversely proportional to acceleration due to gravity. T proportional to root L, T proportional to 1 by root G, where L is the length of the pendulum and G is the acceleration due to gravity. At the same time, here we have seen potential energy is maximum. Where it is maximum? At the extreme point. Kinetic energy of the particle is 0. Where it is 0? At the extreme points. Right? At the same time, if kinetic energy is 0, velocity of the particle is also 0. Where it is? Again at the extreme point. Right? At the same time, restoring force acting on the particle is again maximum. All these things, they are at the extreme positions. So in order to complete one oscillation, that is what you call it as time period. And the time period of a simple pendulum is given by T equal to 2 pi under root L by G, where from this particular equation you can write that T is directly proportional to square root of its length and T is directly proportional to under root 1 by G, where G is acceleration due to gravity. And this particular acceleration due to gravity, it depends, or it varies from place to place. Acceleration due to gravity, it varies from place to place, how it changes. Now here we're talking about the case of time period of a simple pendulum. The time period of a simple pendulum is given by T equal to 2 pi under root L by G. On increasing the length, if at all you increase the length of a pendulum, then time period increases. Why it is increasing? Because time period and length both are directly proportional to one another. Suppose that if the length of a pendulum is increased by 2 times, then the time period increases by root 2 times. If the length is doubled, if the length of a pendulum is doubled, then the time period increases by root 2 times. At the same time, when simple pendulum, here this is a different cases where you are placed the simple pendulum. When simple pendulum is placed at equator, when simple pendulum is placed at poles, right? At the same time, the time period of a simple pendulum where at the center of Earth. Different cases, we'll see all these things. Now, first thing, we talk about the shape of Earth. When you're talking about the case of shape of Earth, right. Now, what is the shape of Earth? Basically, we know that the shape of Earth is oblate shape. We say that the shape of Earth is oblate, or else we even say that it's something a geoid shape. Now, what does he mean by this particular oblate as well as what do you mean by this particular geoid shape? The shape is something like this, right? It is bulging at the equator. It is bulging at the sides. Now, along the equator, it is you are having this particular length is more, but whereas near the poles, it's something flat. It's compressed a bit like this. So here you can see that here you are having the equator, along the equator, it's more, but wherein here it is less. Right? This type of shape is what you call it as the oblate shape, or else you call it as the geoid shape. Now here it's very much clear. Along the equatorial distance, right? Along the equator, the distance is something around 12,756 kilometers, right? But wherein along the poles from North Pole to South Pole, this is something around 12,714 kilometers. Here it is 756. Here it is 714. At difference of almost something around 42 kilometers. right? So along the poles, the radius is less. Along the equator, the radius is more. Now, based on this particular thing, based on this particular parameter, the value of G changes. Now, suppose that when you take in the case of Earth, right, a spherical shape, right? So when you taking this, now if this is what you're calling it as the center of Earth, from center to this particular point, this is what you call it as radius. Now we know that in the case of Earth, this particular value is less. Near the poles, the value is less. Since this is compressed a bit, the value is less. So here the radius is something like this. This is the radius along the poles. This is the radius along the equator. Radius along the equator, and this is the radius along the poles. Now, from the diagram, it is very much evident that the radius along the equator is more when compared to radius along the poles. Now we have got one equation, G equal to Gm by r square. G equal to Gm by r square. This is an equation which is connecting the acceleration due to gravity and the radius of Earth. This is an equation which is connecting acceleration due to gravity and radius of Earth. Now from this, it's very much clear that G and R both are inversely proportional to one another. If the value of R is decreasing, then G value will increase. If R value is increasing, then G value will decrease. If R value is increasing, then G value will decrease. Now based on this particular thing, right, based on this particular thing, the basic equation for time period, T equal to 2 pi under root L by G. T equal to 2 pi under root L by G. If G value is less, right, or else we will see clearly. Now here in this particular case, when I'm talking about the case of equator, first I'll talk about the case of equator. So near the equator, R value is maximum. Near equator, R value is maximum. Just a second, I will erase this completely. Right. Then, now here, near the equator, this is along the poles, this is along the equator. So near the equator, the radius is maximum. At the same time, since near the poles, the shape is something like this, right? It's flat at the poles. As a result of which, along the poles, the radius is something like this, right? Now, equator. Near the equator, the radius value is maximum. Near the equator, the radius value is maximum. Here we have got two different equations, right? So what is the first equation? T equal to 2 pi under root L by G. At the same time, you have got one more equation which is connecting acceleration due to gravity and radius of Earth, G equal to Gm by r square. Now we'll write this based on that particular formulas. The first one, the radius along the equator is maximum. Radius along the equator is maximum. R and G both are inversely proportional. If R is maximum, then G value is minimum. If R value is maximum, then G value is minimum. If G value is minimum, then what happens to time period? Time period will be maximum. So along the equator, time period is maximum. At the same time, you go for the case of poles. When you talk about the case of poles, near the poles, R value is less. From the diagram, which it is very much clear that the radius along the equator is more when compared to radius along the poles. So near the poles, R value minimum. If R value is minimum, then G value maximum. Then G value is maximum. If G value is maximum from this particular relation, then what happens? Time period. Time period is minimum, since time period and G value both are inversely proportional to one another. Suppose that if at all you are talking about the case of center of Earth, right? At the center of earth, the value of G is equal to 0. At the center of earth, G value is equal to 0. If G value is equal to 0, then what happens to time period? Time period will become infinity. At the center of earth, time period will become equal to infinity. Now these are some cases, right? So near the equator, R value is maximum, time period value is maximum, G value is minimum. And along the poles, time period is minimum. Along the at the center of earth, time period is infinity, right? At the same time, suppose that if a person is moving, right, if at all a person is moving from north pole to south equator, if a person is moving from north pole to equator, then what happens to the time period, right? Or else first we'll discuss about the G values. When a person is moving from north pole to equator, then in that particular case G value continuously increases. If G value increases, then what happens to time period? It decreases, right? Then if that particular case, it just keeps on decreasing. Now there in that particular case, whenever you are moving from north pole to south pole, whenever you are moving from north pole to south pole, right, there in that particular case, the time period, the G value, it just keeps on decreasing, right? Now why it is decreasing? Because near the equator, the G value, R value, near the equator, R value is maximum. If R is maximum, G value is minimum. So I'll just repeat that particular point. Suppose that if a particular person is moving from north pole to south pole, from north pole to south pole. So near the north pole, first we talk about the case of north pole. So near the poles, what is the value of G? Near the poles, the value of G is maximum. Near the equator, the value of G is minimum. So it means that you are moving from maximum value to minimum value. So when you are moving from maximum value to minimum value, when you are moving from north pole to south pole, the acceleration due to gravity, it decreases. It decreases. When G value is decreasing, time period value will increase. So when you are moving from north pole to south pole, G value decreases, time period value, it increases. At the same time, suppose that if you are moving from equator towards the poles, when you are moving from equator towards the poles, the G value, it increases. The G value, it increases. So here when you are moving from equator G value is minimum, poles G value is maximum. So when you are moving from equator towards the poles, G value increases. If G value increases, then time period value decreases. Time period value, it decreases, right? At the same time, suppose that you are taking a bucket of water. In a bucket of water, you are placing a simple pendulum. A pendulum is placed in a bucket of water. When a pendulum is placed in a bucket of water, what happens to the time period? It decreases. Sorry, when a simple pendulum is placed in a bucket of water, the time period value will increase. When a simple pendulum is placed in a bucket of water, the time period value will increase, right? At the same time, when a simple pendulum is placed on the surface of moon, when a simple pendulum is placed on the surface of moon, then in that particular case, the time period will again increase. When a simple pendulum is placed on the surface of moon, the time period will again increase. Now on the surface of moon, we know that the value of G on the surface of moon is 1/6 of the value of G on earth. The value of G on the surface of moon is 1/6 of the value of G on earth. So on earth, the value of G is 9.8. So 9.8 by 6 approximately, it's something around 1.6. So on the surface of earth, 9.8 by 6. On the surface of moon, it is 1.6 meters per second square. Right? So if G value is decreasing, on the surface of moon, G value is less. So we know the basic equation. What is the basic equation? T equal to 2 pi under root L by G. So if G value is decreasing, then time period value, it increases. So whenever a simple pendulum is placed on the surface of moon, time period increases because G value decreases. Whenever a simple pendulum is placed in a bucket of water, time period increases. It increases because of the fluid friction. It increases because of fluid friction. The friction that is exerted, the frictional forces that are exerted by the fluids, as a result of which time period increases. Whenever a simple pendulum is placed in a bucket of water or liquid, in that particular case, time period increases. At the same time, whenever you're talking about a simple pendulum, suppose that if at all the mass of a simple pendulum is doubled, the mass is doubled or tripled or quadrupled. For example, first we'll talk about doubled. If at all the mass of a simple pendulum is doubled, it is increased from some 100 grams to 200 grams, then what happens to time period? If the mass of a simple pendulum is doubled, then the time period of a simple pendulum will remain unchanged. If the mass of a simple pendulum is doubled or tripled, I am talking about the mass of the object, but I am not talking about the weight of the object. We all know the basic difference. Mass and weight both are different. Weight equal to mass multiplied by acceleration due to gravity. So, if at all the mass of the simple pendulum is doubled, then the time period will remain unchanged. Time period will not change. The reason is that time period of a simple pendulum is given by T equal to 2 pi under root L by G. It is dependent on only two factors. What are they? One is length, the other one is acceleration due to gravity. But it is not dependent upon mass. That is the reason why, even though if at all the mass of a simple pendulum is doubled or tripled or quadrupled, the time period of a simple pendulum will not change. Right? Now at the same time, suppose that the simple pendulum placed in different cases. You're talking about the case of a lift. Right? Now in this particular lift, I'm having a simple pendulum which is attached here. A simple pendulum which is placed in a lift. Suppose that if the lift is moving upwards, then what happens to time period? If a simple pendulum when placed in a lift moving in upwards, what happens to time period? Right? When the lift is moving upwards, since it is moving against the gravity, the value of G will decrease. Right? The basic equation T equal to 2 pi under root L by G. If G value is decreasing, then time period will increase. So when a simple pendulum which is placed in a lift moving upwards, the time period will increase. At the same time, suppose that if the lift is moving downwards, then the value of acceleration due to gravity will increase. If G value is increasing, then time period value will decrease. Right? This is the cases. Then at the same time, you talk about a person. About a person who is standing in a lift. Now if the lift is moving upwards, when a person who is standing in a lift, right, and the lift is moving upwards, if the lift is moving upward, then in that particular case, the apparent weight of the person appears to increase. Now whenever you talk about the weight of a person, you have got two different weights. One is apparent weight, the other one is real weight. Now when I am standing here in this particular classroom, this is what you call as the real weight. When you are moving on a vehicle, at a speed of something around 80, 100 or 120, that is what you call it as apparent weight. Now for example, suppose that if you are moving on any particular bike at a speed of 100 or 120, the weight of the vehicle appears to be less. You feel like almost flying in air. But the moment you are moving on a bike at a speed of 20 or 30, you start feeling heavy. At a speed of 100, 120, you start feeling lighter and lighter. That is the reason why at that particular speed, it is difficult to control a vehicle. Right? The moment accident takes place, it leads to more amount of damage, because at that particular speed, the weight appears to be less, and at the same time, it is difficult to control that particular situation. Now that particular weight is what you call as apparent weight. If the lift is moving upwards, in that particular case, apparent weight will be more than the real weight. Suppose that if a person is weighing something around 60 kgs, if the lift is moving upwards, the person will experience a weight of around something around 60.5 kgs or 60.6 kgs. right? Apparent weight will be more than real weight. And if the lift is moving downwards, then in that particular case, apparent weight will be less than real weight. If the lift is moving downwards. Suppose that if the lift is present in the 4th floor or 10th floor, but it is stationary. The lift is not moving, it is the 10th floor, it is stationary. Then in that particular case, apparent weight and real weight both will be equal. Right? At the same time, suppose that if the lift is falling freely, which means this particular wire is broken and the lift falls freely, then in that particular case, the person in the lift will experience weightlessness. If the lift wire is broken down and the lift is falling freely, then in that particular case, the person in the lift will experience weightlessness. Right? So this is something about the case of your mechanics as well as the fluid mechanics. So in the case of mechanics, first we started with the case of your units. Then we moved on to scalars and vectors. Then we moved on to kinematics. So in the case of kinematics, we discussed what is distance, what is displacement, what is velocity, what is acceleration. Then we moved on to the case of dynamics, in which we discussed what is the reason why the object is coming to rest. What is the reason why the object is coming into motion? So in the case of mechanics, we discussed what is Newton's laws, right? Work, power, energy, what is friction, then what is centrifugal force, centripetal force, the different types of forces that we are experiencing. Then moving on to the case of your fluid mechanics, we discussed what is Archimedes principle, what is atmospheric pressure, what is surface tension, and finally the case of your simple harmonic motion. So this is something about the case of your mechanics in brief. Right? So my suggestion for you guys is that try to practice more number of questions. At the same time, concentrate on the application as well as the concepts. Right? There is no need for reading the formulas or by hearting the formulas. The thing is that you need to focus on concept as well as the application part of you, and at the same time more number of examples. And those who are preparing especially for examples, we need to focus a lot on examples. Right? That's it. Thank you.